reacts to a magnet. It's been a year since part 4 and I have saved up for some new elements. This time I will test all elements in the platinum group and a few others. These noble precious metals are very expensive, so the samples will be small on my budget. But they all weigh around 1 gram, which has some advantages. More about that later. If you haven't watched the first 4 episodes in this series, I suggest that you do. Or at least watch part 4 before this, since I've got a brush up on the terms ferro, para and diamagnetism in it. Let's go. First test is my classic water bath test, where the styrofoam boat doesn't have a noticeable reaction to the neodymium magnet. But this test is so sensitive that it easily detects the magnetism of even 1 gram samples. For 5 of the elements in this new set, I've already shown you their magnetism, but let's quickly test these new specimens for good measure. This ruthenium sample is clearly attracted to the magnet, but does not stick to it, evidence that ruthenium is paramagnetic. Silver, on the other hand, is repelled by the magnet. It doesn't matter which pole of the magnet I use, since silver is diamagnetic and will always repel an external magnetic field. Iridium is weakly attracted to the magnet. And so is osmium. They are both slightly paramagnetic. 24 karat gold is still diamagnetic and repelled by a magnet, even with only 1 gram of it. It isn't exactly a powerful reaction. Diamagnetism is always weak, and bismuth, for example, is still 10 times as diamagnetic as gold. Alright, let's move on to the elements I have not tested before. Starting with one just outside the platinum group. Rhenium is a rare metal, rarer than gold. It is very difficult to melt. In fact, it has the 3rd highest melting point of the elements, only topped by tungsten and carbon. But of all elements, rhenium has the highest boiling point, so it really doesn't like to be turned into a gas. This high resistance to heat is useful in jet and rocket engines, and rhenium's main usage is in jet engines as part of a nickel superalloy. Rhenium is clearly paramagnetic. Its official value for magnetic susceptibility is +67. Next up is rhodium, which is also very rare. Natural rhodium only has 1 isotope, so this is actually a rhodium-103 sample with 58 neutrons in every nucleus. It is mainly used as a reduction catalyst alongside platinum in catalytic converters, which make our cars less polluting. Rhodium is also used as a neutron detector in the cores of nuclear reactors, since it will work well for sensitive SPND. Rhodium is drawn towards the magnet, making it paramagnetic. The strongest reaction to a magnet so far in the platinum group. But look how palladium reacts. Even at distance there's a clear attraction. Close to the magnet, it really locks onto its target. Palladium is primarily used in catalytic converters as well, but in a second stage as an oxidation catalyst. Another common use for palladium is in capacitors for electronic equipment. Looking at the reaction, it is no surprise that palladium officially is 5 times as paramagnetic as rhodium. At +540, it is only some of the lanthanides that have stronger paramagnetism at room temperature. The final element is the one that the platinum group is named after. Platinum is a very important metal with a lot of uses. It is one of the least reactive elements and at the same time an efficient catalyst in, for example, catalytic converters, but also for catalytic reforming in the petroleum industry as one of the processes for turning crude oil into gasoline for your car. Jewelry is another common use for platinum, since it is highly unreactive and valuable like gold. Being very rare, very important and therefore very expensive, it is one of only 4 metals to have its own currency code. At times, platinum is more expensive than gold. Platinum is definitely attracted by the magnet, just not as much as palladium. It is the 2nd strongest paramagnetism of the group though. This is where the video would usually end. I have now shown you 69 different elements near a magnet and their official value for magnetic susceptibility as proven by scientists in a lab. However, the 9 samples in this video are all melted pellets weighing around 1 gram each. That makes them useful for showing the property density. Here I have arranged them in order of increasing density with the 4 densest of all elements to the right. Just for reference, lead, which we usually think of as dense and heavy, is around 11 gram per cubic centimeter. Yet its density only beats silver in this chart. Lead is quite lightweight compared to the 5 to the right. You can clearly see the big jump in density between rhodium and gold, where the pellets get smaller but still weigh 1 gram. Okay, the silver sample is a little overweight. It is so cheap in this comparison that the seller didn't bother about the almost 0.2 gram too much. They are still close enough in weight that I'm gonna attempt to quantify the amount of magnetic attraction in these samples with my ghetto-style tests. One test will be the time it takes a giant neodymium magnet to attract the sample from a fixed distance. A faster time indicates a more paramagnetic sample. The other test is to measure the pull force in milligrams generated near the sphere magnet. To get a steady reading from such a sensitive setup, I'll use this rig made from Lego and a 40 gram zinc counterweight. The scale is an unbranded inexpensive one I bought on eBay, but it's close to the seller's specified weight, measured on a quality scale down to tenths of milligrams. Due to the paramagnetism in the sample, it is lifted away from the scale by the magnet. All I have to do is find the highest possible steady minus reading. For rhodium, it is a pull force of 67 milligrams, less than the weight of a toothpick. Palladium is of course much more responsive. It quickly goes to the magnet. And the pull force is a more respectable 332 milligrams, almost a third of the sample's weight. Iridium and osmium were very slow, and I couldn't even detect a lift on the milligram scale. Rhenium and ruthenium did a lot better. They were close to rhodium's time. Their pull force were also just about detectable. The final element before I take a closer look at the test results is platinum. I tried this 10 times with each element since this test is quite crude and manual with human errors as a possibility. It finds the magnet rather quickly. Let's look at the results. Here are the 10 times for each element, except the diamagnetic silver and gold. They repel a magnet, so they are disqualified for this test. The times are scattered, so let's clean them up by removing the 2 fastest and slowest times for every element. I may have pushed the sample a little when I released it, or just been too fast or too slow on the stopwatch. The average time for the 6 counting makes it easier to see the difference between the elements. Let's sort them from fastest to slowest time and adjust for the slightly different weights. Physics doesn't scale well, but this should be better than not correcting for weight at all. I am pleased with this result. It's not perfect, but the elements are at least in the right order. Considering how weak the forces are, especially in such small samples, it's nice to be able to confirm the scientific values in a simple setup at my home. So how about the pull force test? Let me show silver and gold, because this test works with diamagnetism too. I just have to look for the highest plus reading without touching the sample. Silver repels the magnet with a force of 13 milligrams. And gold? The smaller gold sample repels with a force of 10 milligrams. Well, the scale seems to struggle with the weak forces. The final result is not as good as the water bath test. But overall, it still gives me some extra confidence in the official values. The cheap scale just isn't very useful with small samples when the magnetic susceptibility is below 100. Alright, time for me to save up for some of the last available elements. I don't like asking for money, and I won't this time either. What I do ask for is, could you please click the thumbs up button. Let me know if you like this video and want to see part 6. Thanks for watching.